suppose.
Yeah.
Okay, so let's start. So Jérôme, will you share your screen?
Yeah, oh, yes. Okay. So this.
It worked the first time around.
I have to go back to yes. Yes, share screen. Okay. Is that okay? Can you see it? Can you see the screen?
No, it's perfect.
Yes.
Okay. Okay, very good. Okay.
Okay, so
I can't see the chat. Okay, now I can see the chat. Okay, thank you very much. Thank you very much. Indeed, I mean, I thought that we were back in 2006 as well. That's weird. That's good. That's good and weird at the same time. Okay, so this is a survey talk, which means that I'm going to talk about a lot of things, but not in a very technical way. So don't expect a technical talk. I mean, there will be plenty of examples and high-level comments and not much technical. This is a survey paper. There is a survey paper that comes with the talk and which will be presented at ICHCAI at some point. I don't know where this will take place. It's on my webpage. I will give very few references during the talk because that would mean too many references. So only at very specific points I will give references, but they are in the paper. So sorry for those I should cite during the talk and I won't. So first and importantly, I mean, I would like to recall that Jérôme Monod passed away last December. He was a member of LAMSAD. Many of you know him. Some of you don't know him because he could not travel because of his handicap. Most of the works I did on this topic. Social choice under incomplete knowledge, incomplete preferences, was done with him and other colleagues. So I thought it was it was the right time to talk about him. Okay, so let's start with very simple example. So suppose that we have 9 voters, but for some reason one of the 9 voters has not reported their vote yet. So if the rule is Borda, then we can compute the partial Borda scores, and it's very easy to see that it's needless asking the last voter to give preferences. We know the outcome, right? We know that B is the winner. If the rule is plurality, on the other hand, here are the partial scores. So we see that we don't know who the winner is, but we know something. We know, and actually all we know is that A and C can win, depending on which of both the last voter prefers. And this is all we know. So what I'm going to talk about is about generalizations of that. If you already know about possible and necessary winners, what I suggest is that you come back after half of the talk duration. Okay, second example. Suppose that all we know, I mean, we have some partial knowledge about the voters' preferences, but that is different. I mean, this partial knowledge is different. Here we know only the tops. We know that a fraction alpha of the voters has A on the top, and then beta has B on the top, and so on. And we assume, without loss of generality, that these alpha, beta, gamma, delta are ranked in this order, and that alpha is strictly larger than gamma. Otherwise, that would be too simple. The question is, when does C have a chance to be one of the winners, possibly tied with others, depending on the voting rule? And below, I'm writing conditions, okay? And I would like you to guess which voting rules which correspond to the condition. So you can use the chat, okay? So can you think of a voting rule for which C has no chance to be a co-winner, whatever the completion of these preferences? Okay, so use the chat. It works. Yes, okay, so I see already someone who said plurality. Indeed, plurality, it's very easy to see that we know the outcome already. It cannot be C. Can you find a rule such that the C is always among the possible winners. I mean, C always have a chance to be a possible winner, a winner. Yeah, constant rule, of course. Yeah, but yeah, something more. Yeah. Nomination. Yeah, something more classical. A scoring rule. Yeah, veto. Okay, anti-plurality, veto. Yeah. But you made other suggestions that work, of course, but I was expecting anti-plurality. What about that one? Yeah, that one, it smells like what? It smells like a well-known rule. What did I okay. Okay, this one, yeah. Okay, so this one is border. This one, okay. What about the next one? I see questions I would like to answer. Okay. What about, okay, so I don't see if you are saying something on the chat, but anyway, this one will work actually for all Condorcet consistent rules. What about this one? It seems like no, but okay, I understand. Okay. Okay, I can't see the chat anymore, or maybe it is that nobody writes on the chat. Nobody is writing in the chat. Okay, so this one, anyone has an idea? Okay, nobody is writing. No, not quite. Yes, plurality runoff. Yeah, yeah. And the last one. Someone mentioned it before, okay. At the wrong place. I can explain actually. Yes, STV. Okay, let me explain the last two. Okay, plurality with runoff here because we need C to get to the final, and for this we need beta and gamma to be equal. Otherwise, the final would be between alpha and beta. And then we need C to win against A, and for this to be possible, we need that alpha should not be larger than 1/2. STV. STV, we need, so we know that D will be eliminated first, that's for sure. Then we need C not to be eliminated second. And for this, in the best case, the votes for D will transfer to C, and these are these votes. And this number of votes should be at least the number of votes for B. And so this ensures that C has a chance not to be eliminated at the second stage. And this means that C has a chance to go until the final stage. Okay, let me continue. Okay, so more generally, so we assume that for each voter, we have a partial order Pi over the set of candidates. Okay, this is an incomplete preference. And P is the collection of P1, P2, Pn. This is an incomplete preference profile. What we call a completion of P is a tuple of total rank of complete rankings, such that each Ti is an extension, a linear order extending Pi. Right? And then we take a voting rule, resolute or irresolute, and we say that C is a possible winner if, for some completion of P, C is a winner. And C is a necessary winner if C is a winner in every completion of P. Okay, maybe I should get rid of that. Okay, so example. So we have 3 voters. The first voter says only that A is on the top. It doesn't say which of B and C she prefers. The second voter says that B is preferred to A, but she doesn't speak about C. And the third voter reports a complete ranking. So we consider the completion for each of these partial votes. So this one has 2 completions, this one has 3, this one has 1. So this makes a product of 6 profile completions. They are there. And for each of these completions, I compute the border winners. Sometimes there are several tied winners, sometimes only one, and then I collect them and I get the possible border winners. Okay, everyone here is a possible border winner, and there is no necessary border winner because there is no one that appears everywhere in all completions. But then if I learn that the second voter actually prefers A to C, then out of the 6 completions, I get only 2 that remain. And then we get that in all the possible completions that remain, A is the border winner. So we have a necessary border winner, which means that we can stop elicitation and we can output the winner. Then I want to talk about some particular cases and context in which we get such incomplete preferences. The first one is missing votes. Missing votes is the context where we have n minus k voters who have reported a full ranking, okay, these voters, and the other k has reported nothing, okay, these ones. Yeah. The first example I showed before, it was that kind. It has also a strategic interpretation because X is a possible winner if the last k voters have a way of casting their votes such that X wins. So this is called a constructive manipulation for X. And likewise, X is a necessary winner if those voters do not have a way of avoiding that X wins. This is the absence of destructive manipulation against X. Another context is missing candidates. Missing candidates, an example of context where it appears is that doodle poll where first you vote on the first set of dates, and then we realize that new dates become possible. Or a hiring committee where we interviewed some candidates or applicants, a preliminary vote is done, and then some new applicants are interviewed. And more generally, this is the context where voters have expressed their votes on a subset of candidates, on a set of candidates, and then some new candidates come in. And of course, we don't know what the voters think of these new candidates. So here, this is an example where we know the votes about A, B, C, but we don't know what the voters think about D and E. An example of that. Of course, I mean, all these new candidates, I mean, for reasonable voting rules, all these new candidates, they should be possible winners. But the question is, who among the old candidates is a possible winner? So suppose we take the plurality rule with this tie-breaking priority, and we initially have ABC as candidates, and then we have one new candidate, Y, that comes in. And we already know the votes, I mean, the voters have already reported preferences about ABC, and we know that the partial plurality, we know that plurality scores for ABC distribute that way. These are the scores before Y is taken into account. The question is, who can win? Can A win? Well, yes, of course, because if nobody votes for Y, if everyone who was voting for A still votes for A, then A is a winner. Can B win? Yes, no? Who thinks, can you write in the chat? Yes, no, can B win? Okay, I see some yeses, of course. If we get 2 of the voters who voted for A now vote for Y, then B has more votes than A and B wins. Can C win? On the chat? No, because if we do that, if we do the same trick, then we need 3 voters who voted for A and 2 who voted for B to vote for Y, and then that makes 5 votes for Y, and so C cannot win. Yeah. Another context is what I call incomplete lists and what other authors call partial chains. Voters rank only the candidates they know. For instance, the films they've seen, the candidates they have interviewed, and so on, the restaurants, hotels. And there are plenty of results about this in a recent paper I do not cite on my survey paper, so I thought I should cite it here. Something that looks similar to that, but which is in fact very different, is truncated ballots. These are also partial chains, but of a very different type. It's that, I mean, actually these are not partial chains. This means that each voter gives their top K candidates for a K that may depend on the voter, and they don't say how they rank the candidates below, but we know that the candidates below are below them. So this is very useful for incremental preference elicitation. Suppose that we have the border rule, and so we want to compute the winner, to output the winner with little communication. We can ask first the voters to give their top, okay? Suppose they give their top. Okay? Do we have enough information to know the winner? No, here we have no necessary winner. So we can ask voters to give their second best, okay? Suppose they give that. And then it's easy to see that the output, that there is a necessary winner, that is B, okay? That there is no chance that B cannot be in the set of winners. And we can stop here, we have a necessary winner. Okay? Another context is partition preferences, what I call multichotomies as well, where you just, this is very general. I mean, every vote should be a weak order, except, not exactly a weak order. It should be a set of clusters of candidates where in each cluster, the candidates are incomparable, okay? With special examples where we have here dichotomies, but elements on one set cannot be compared. These ones are not comparable, these ones are not comparable, and so on. So there is plenty of results in that paper, which I don't cite either. And a special case of that, a special case first is truncated ballots, but another special case is K-cotomies, where each voter gives exactly K-ordered subsets. And an even more special case is approval ballots or dichotomies, where each voter gives an approval ballot, but not saying how they compare the approved candidates and the non-approved candidates. Okay, so these candidates are not comparable. We don't know how they are compared, and same for these ones. An interesting questions about that when we have such partial orders, I mean dichotomies, is for which rules are all approval winners guaranteed to be possible winners? And we have some results with built figure that say actually that basically, I mean, more or less half of the positional scoring rules satisfy that property, and the other half does not satisfy that property. And voting rules that are close to anti-plurality fail to satisfy that property. For anti-plurality, it's very easy to see. If we have this profile, then D is the approval winner, of course, but it cannot be the anti-plurality winner because at least one of, because D is at the bottom of one vote, and at least one of ABC is at the bottom of 0 votes. Okay? Cloning. Cloning is a special kind of context where we know the voters' preferences over a set of candidates, but then we decide to clone one candidate. So candidate A is cloned into A1, A0, A1, and A2, for instance. We know that the voters will rank these clones contiguously, but we don't know how. Okay. If the rule is clone proof, then the problem is trivial, but otherwise it's highly non-trivial. And there are works on that are cited in the paper. Okay, so all these contexts, I mean, they come in a nice taxonomy. So there would perhaps be other meaningful contexts. I don't know, I mean, you have to tell me. And what's interesting is that if we fix a voting rule, we can try to see where the problem is easy to solve, where the problem is NP hard, and where we don't know. So for the border rule, as far as I know, this is the map, okay? And there are cases where we don't know. Okay, there are things about variance of extension of the framework, and it's in the paper, not in the talk. So why do we have such incomplete preferences? Well, either because of intrinsic incomparability, because it makes no sense for the agents to compare X and Y, because of epistemic incomparability, because the agent lacks knowledge, okay? Or because of frugality, because the elicitation protocol asks the agents to report only a small part of their preferences. either because it would be cognitively too demanding for agents to specify complete preferences, or because of the huge number of alternatives, and that implies it would be infeasible to ask agents to specify complete preferences. And we talk about that later if I have time to do that. And more generally, we can, this is related to, of course, modal logics, epistemic logics, for those who know about that. And so we could call that modal concepts in social choice. We have a collective decision-making, oh, okay, 3 or 4 minutes again. A collective decision setting, agents express incomplete preferences, and we have then possible words that are completions of these incomplete preferences, and we take a Boolean property, such as one of these, and we can ask if necessarily phi, which means phi holds in all possible words, or possibly phi holds in some possible words. Okay, let me talk in 3 minutes about another application, which is fair division of indivisible items. Okay, we have a set of agents, a set of indivisible items. This is an allocation, okay, where pi1 is the share for agent 1 and so on. Every agent has a preference relation, which is a weak order over the set of all subsets of items. But the problem is that there are very many subsets of items. And so we need to find a frugal way, a cheap way for agents to express preferences over sets of items. A choice is to use the responsive extension, which is the smallest preference relation that is monotonic and responsive. No time to explain, many of you know. An example, this is the responsive extension for 3 items, okay? So we extend the preference relation over single objects to subset of objects, okay? And it has this form, I mean, the responsive extensions for 3 items, this is for 4 items. You see it's a partial order. It's a nice partial order, okay? It's a partial order. So because it's a partial order, then we can do the same trick. I mean, we start with preference relation over single objects. It's very cheap to elicit. Okay? Then we compute the responsive extensions. We get a collection of partial orders, and then the possible words are the complete extensions of these partial orders. Example, 3 preference relations over single objects. Is there necessarily a free allocation? Well, no, because if we give A to 1, then there are possible words where 2 prefers pi of 1 to pi of 2. If 2 values A very, very much and the rest very little, then 2 will envy 1, and vice versa. So there is no necessary NV-free allocation. Is there a possibly NV-free allocation? Yes, this allocation is NV-free. Why? Because if 1 and 3 prefer their top objects very much, and they prefer it to any other subset of objects, okay, then they are not envious. And if 2 has simply a preference for having more objects, then she would not be envious either. Okay, and let's assume that one of the agents is going away, 1 leaves, and so is this allocation necessarily NV-free? Yes, because you can see that 2 prefers AD to BCF, actually, because ADE stochastically dominates BCF with respect to 2's preference, and the same for 3. And the last thing is about Pareto efficiency. So is pi possibly Pareto efficient? Yes, so we have a simple graph characterization. And is pi necessarily Pareto efficient? And this is my last slide. Well, almost, I mean, there is one more slide. So pi is not necessarily Pareto efficient because there are possible words where this allocation, C, D, E, F, A, B, Pareto dominates this one. Okay, and there is a nice characterization. There is a characterization in the paper. Okay, so this is the last slide. Just to mention that there are other papers I didn't talk about that bear on other subfields of social choice that consider similar necessary and possible solution concepts. So, what should I do now? Okay.
So let's maybe unmute ourselves for a round of applause. so I can see that these slides also illustrate that the concepts of possible and necessary also apply to slide design. Thanks.
Yes.
So, right. So I didn't see any questions to the speaker in the chat. There was a question from Omar in the beginning, but I think that was a clarification question that hopefully got resolved later on. Or
Yes,
Omar,
yes,
do
I
you
got
want to ask
yeah.
it?
Yes, yes.
Yeah, I got it later. Yeah.
Omer, yeah, I know.
I understood it later. It took me a while, but I got what you meant.
Yeah, yeah. Okay, good.
Okay, so now let's continue with questions. So I think if we do it in voice mode, it can get kind of too loud and unruly. So either raise your hand or ask your question in the chat. Anyone? Hope I can see raised hands, so I don't see any at the moment. Okay, so Ulle, Jérôme, can you see the questions?
Major research challenges ahead. Yes, there are open questions. I realize there are quite many open questions, and then there are new. I mean, I don't know. You could explore multi-winner elections, and then we could. I mean, probably what would be interesting is to use that for the elicitation process. I mean, you want to make it easy for agents to report their preferences. You would like them to report as little preferences, as little communication, as little information as possible, and so have interactive algorithms that stop as soon as there is a necessary winner, and finding sophisticated protocols to know exactly which information to ask and when. There are a few works about that, but there needs to be much more, I believe.
Thanks. I see a raised hand from John Weimark.
Okay. When you started talking about missing voters and their preferences, you talked about collective manipulability.
Yes, yes, that's exactly that. Yes, yes.
Yes, and you know, there's a methodology used in studying strategy-proof social choice rules, which bears on this. It's called the option set methodology. And whether you're looking at a particular rule or asking what rules satisfy a list of properties, a standard way of approaching that problem is to say, let's fix a set of voters. These are your missing voters. And ask, what's the set of possible outcomes that you can get for some profile of the preferences of the other people?
Yes, yes. That's exactly that. Yes, yes.
Yeah, so it's just a comment rather than a question.
Thanks. So there's another question in the chat.
Application with data, what do you mean, Vincent? Vincent?
Sorry. Imagine you have some partial information, then you have more information. So could you say something that by you may say sometimes it's so you always look at the more extreme cases to see if it's you look at all the cases to see if you have a possible winner, but maybe very unlikely that C is a possible winner. There's a correlation about the votes, even if they are partial.
Yes,
so
yes,
if
yes.
you go for more and more data, maybe even if C might be a possible winner, there's no chance it will be a possible winner when you look at all the data.
Thank you, Vincent. That's a very good question. Yeah, that's a very good question. Indeed, I mean, I assume that all preferences are equally possible, and actually that relates to the next question by Klaus. Of course, I mean, in practice, actually, we have distributions over votes, and we see, well, sometimes we even have domain restrictions so that we should not consider all completions, but we also have distributions over votes. And then Klaus asked introduce probabilities. Oh, well, there is at least one word, probably a few more, about what people call probable winners, where you count completions in which X is a winner. But of course, again, I mean, it would be more interesting to start with the distribution over profiles, and then to output the candidate that maximizes the probability to be elected. So the conclusion much easier when some of the candidates cancel themselves.
Can I just?
Yes, Klaus, yeah.
One could also imagine something like very unlikely, nearly necessary. So where we're not really interested in, you don't believe in the probabilities, but you want to say, well, except for circumstances that would be, this one would or this one wouldn't. That would be, seems to be more sensible actually use of problem.
Yeah, definitely yes. In low stake context, where I mean it's not a big it's not a big issue if you elect someone even if it's not a necessary winner. In a political election, probably you should be sure. Bill, assume voter only indicates A prefers to B when utility advantage of A exceeds. Ah, okay. I understand the question, but I don't know what to answer. I will answer in private after I think about it.
So I think we are kind of, our overall slot for Jérôme was half an hour and we're approaching the end of that. So I think it's kind of time to stop, maybe unmute ourselves once again for another round of applause. Thanks, Jérôme, for a great talk. And now it's time for the part of our seminar to at least find the most exciting, the coffee break. Right, so the way this works is we will be randomly distributed to breakout rooms. So feel free. So that will be for 10 minutes. So you're not obliged to go. It would be nice if people join because that's a chance to meet your fellow seminar participants. Right, and you'll have a chance to, to chat to others for about 10 minutes. And then we will be back for the second talk, for Ulle's talk. So I trust that Dominic will now press the magic button and distribute us into groups.
I will do that. We have now quite a lot larger rooms, so I hope people don't talk over each other, but it should be fun.
I'm back. So are we starting in what, in a minute or two? Okay, welcome back, everyone. So it's time for our second talk, which will be given by Ulle. Ulle, are you able to share your screen?
We'll find out.
Okay, perfect. Okay, so the second talk is by Ulle. So it's a paper called Axiomatic Justification of Election Outcomes, which I believe has been published by now. Well, Ulle will tell us all about it. So welcome, Ulle. You have 20+ minutes for a talk.
Thank you very much. So yes, just double checking. So you can see my slides. You can see me. You can hear me. All right, that's excellent conditions for giving a talk. So I will go ahead. Indeed, this is about a paper that has just appeared in the proceedings of AMAS. The link is on the website. It's joint work with Arthur Boixel, also from Amsterdam, and he's also in the audience today. And what I want to talk about is the question of what does it mean to justify that some outcome of an election might be a good one. You're given the preferences of the voters and you say, well, how about this outcome? How can you justify that it's a good outcome? And I will spend most of the talk just pondering that question, and hopefully you will agree that we've come up with a nice idea how one might want to do that. So I'll start with a little example to give you an idea of what the kind of thing we have in mind. I'll then go on to a more formal definition of this concept of justification. In the middle of the talk, I'll spend a bit of time talking about 3 different scenarios where you may want to use this idea. And towards the end, I'll briefly talk about some algorithmic aspects of this, of how you might have a chance to actually compute these justifications. It's quite a complicated thing. So if there are any questions along the way, please do not hesitate to type them into the chat. I have one eye on the chat, and at least that right now, I think I might be able to see when you type something. We'll find out about that. And if not, I'll pick them up afterwards in the question period. And like Jérôme, I had the brilliant idea of including some exercises. I think mine are a bit easier than his, but still I encourage you to try. So whenever you see at the bottom of the screen, it says exercise, feel free to type in the solution if you find it in your chat. And I'll be commenting on those solution attempts. All right, so then I think we have to start with the example. All right, so what you see here is a preference profile. So we have 3 voters, voter number 1, 2, and 3. And they express preferences over alternatives. So the square, the triangle, and the circle, these are alternatives. So for example, the first voter says, I like the square more than the triangle, and I like that one more than the circle. And then when you look at the entirety of this profile of the 3 voters, you may ask yourself, okay, who of these 3 alternatives should win the election? And one way of trying to answer that would be by kind of giving an answer to this exercise down here. Think of a voting rule that you know, maybe that you like, and that would elect one of the alternatives that you think would be a good one. So for example, what might be a voting rule that elects the square? And I see a couple of good answers there. So plurality, for example, would do it. Any Condorcet consistent rule would do it. And there are others that have not been mentioned, like the border rule, for example, would also do it. So indeed, that's not so difficult. So people are able to answer that question. So let's make the question a little bit more difficult. Can you also find a voting rule that would make the triangle win? True approval, yes. Do you know another name for true approval in this particular context? Veto, exactly, or anti-plurality. So there are fewer rules, it seems to me, but there are some rules that would also give the triangle as a winner. And the circle, I'm not so sure whether we're going to find a good rule that makes the circle win, but we could try to think about it. But then, so your first thought of what is a justification might be, okay, I'll take a good voting rule, maybe the border rule elects the square. So I'm going to say that's going to be my justification for electing the square. And if you're wondering why the border rule, then I say, well, just look, there's this eminent professor of mathematics in the sunny state of California. He has like 5 books that all say it's the best rule in the world. So this is a perfectly good justification, you might say. But the problem is that means that people will have to read these books and ideally no other books. And then maybe they're going to buy that. But it's not going to help them really in the here and now to figure out what is a good answer here. So I would like to just directly be able to demonstrate to people why, for example, the square might be a good outcome. And I would like to also explain them why I think so. They will be open, it will be possible for them to disagree with my justification, but it should be a reasonable one. So let me attempt to justify the square as an outcome. We might do it like this. We might say, okay, let's just focus first on the sub-profile where only the first voter votes. Well, if only one voter votes and she likes the square the most, that's a clear winner. Of course, we should elect the square and nothing else. So I'm always going to put a set here because in principle, it could be a set of winners, but there's only one clear winner here. Some of you may know this idea under the name of faithfulness. It's one of the axioms that you will find in some social choice papers. Okay, so that seems pretty clear. Now let's look at the rest of the profile, just the sub-profile down here of voters 2 and 3. If you look at it, this is quite symmetric. So you have here one voter saying circle, triangle, square, and the other one says it exactly the other way around. So with this very strong symmetry, you might say the only thing we could reasonably do is to say everybody should win. And some of you know this idea as the cancellation axiom, which some people think is a good idea. Okay, so then I have analyzed the two subprofiles, and now I can put it all together and say, okay, if in most of the people, when they vote, there would be a perfect tie, and then we add this one more person, and if that person were alone to vote, the square should win. We should think of this one person basically breaking that tie over here, and the square should win. So this would be an instance of something that some of you know as the reinforcement or the consistency axiom. So that would be an example for the kind of justifications that we have in mind. I think it's a good explanation of why that would be a reasonable winner. You can, I think, understand the steps. You can disagree with some of the steps. So we're not saying that you have to absolutely, there's one perfect justification and nothing else can possibly be right. So for example, I personally find this second step here a little bit questionable. So I think it's not crazy, but it's also something that you could say, okay, there's some symmetry here, but it's not a perfect symmetry. So why do I want to make this very strong statement of having everybody win? So you could criticize that, but then you could have a discussion very pointedly just about this one point. And you would maybe not really doubt that. And you would maybe also not really doubt that step. You would just want to discuss about this one. And then you could maybe introduce another principle and say, okay, if I use those principles, I can either find a better justification for the same winner, or maybe I can find a different justification for another winner. But then we're not just saying, I like this rule and that one wins, but I'm able to say, I think this one should win, and here is why, and we can talk about these arguments with each other. So that's the basic idea. All right, so let me try to make that a little bit more formal, what we have in mind. So here's a fairly standard model of social choice functions of voting rules. So we have a set of agents in this set n star. So for example, the three voters from before, they might be the ones that make up this set. They express preferences as strict linear orders, like they did in the example, over alternatives in a set X. And then a voting rule will be something that tells us for any preference profile, ideally which alternative wins, but sometimes there will be a tie. So it has to, sometimes we return a set of alternatives. It's written down formally here. So let's take apart this notation a little bit. So this is the set of linear orders over the set of alternatives. If for a moment I cross that thing out here, then that thing is the set of profiles where everybody in the set N reports a vote. And what I mean by this is the set of profiles where some subset of voters from the big set N star reports a vote. So any such thing is a profile, and it should map into that thing over here. This is the power set of X. So this is the set of all non-empty set of alternatives. And there are a huge number of these voting rules, and some of them will be nicer than others. And when we say a voting rule is nice, it's probably because it satisfies some axiom, like neutrality, saying we should treat all the alternatives in a symmetric way, or the Pareto principle, which says if everybody says A is better than B, whatever you do, you should never elect B amongst the winners. This raises the question maybe of what really is an axiom. I think that's a difficult question, and maybe not just any crazy property you would want to call it an axiom, but once you have decided, okay, this one I want to call an axiom, the next step is, okay, what does it mean exactly? And so for this, we have some simple notation for the interpretation of an axiom. This thing over here, an axiom is really just the set of voting rules that satisfy this axiom. So it will be, this is the set of all voting rules copied from up there. And so interpretation of an axiom is just a subset of that. So for example, the interpretation of the neutrality axiom is a huge set, includes the border rule, the Copeland rule, lots of other rules. Another concept we need is the notion of an instance of an axiom. So this is an application of an axiom to a specific situation. So a specific profile, maybe a specific couple of alternatives, possibly even a specific voter in principle. So again, an instance of an axiom can be in principle anything that you feel you want to call an instance of an axiom. The only thing that we require is that these instances themselves are also axioms. And if I take all the instances of a given axiom and I compute the intersection of the interpretations, I should get the interpretation of the original axiom. So for example, one of the many instances of the Pareto axiom is that if I'm looking at this kind of profile, so this is meant to say two voters, the first voter number 2 says ABC, voter number 5 says BCA, nobody else says anything. For sure, we should not elect C because it's dominated by B, by both of the active voters. So that would be an example for an instance of an axiom, which we can then interpret as the set of all voting rules that satisfy this one aspect of Pareto. All right. Now towards the definition of justification. So what we want to do is the following. We are looking at what we call a corpus of axioms. This might be quite a large set of principles that we think are reasonable, maybe includes anonymity, neutrality, Pareto, Condorcet, reinforcement, anything you can name, maybe some you invented yourself. Principles that we think these seem like good things that we could use as an argument to convince somebody about a voting outcome. We're looking at a concrete profile where everybody in the set N star has voted. And we're asking ourselves, can we justify that the winners of this election should be exactly the alternatives in the set X star? And our idea is that such a justification should have two parts. It should be, first of all, what we call the normative basis. This would be a set of axioms and an explanation, which would be kind of a step-by-step explanation of how these axioms force X star to be exactly the winning set. So formally, a justification will be a pair of sets of axioms, the normative basis and the explanation. And it has to satisfy these four properties. The first one is adequacy. The normative basis has to be drawn from the axioms that we think are reasonable, have to come from our corpus of axioms. The relevance of the explanation says that the explanation should be a set of instances of our axioms in the normative basis. The most important one is explanatoriness. It's a property of the explanation of this set of instances of the axioms. It says that for every rule that satisfies all of these axiom instances in the explanation, it should be the case that exactly X star are the winners for our input profile. And furthermore, this should not be the case if I make the explanation any less powerful. If I remove some of these instances, it should be exactly the right one to explain what I want to explain. And so far I could still make a mistake and kind of basically use an impossibility theorem to explain anything. So we have this final condition of non-triviality, that the set of axioms in my normative basis, they have to admit at least one voting rule that is possible. So there has to be at least one voting rule that exists that satisfies all the axioms that I'm using in my explanation for why I'm saying X star should win. Okay, so that's the idea of a justification. Let me talk a little bit about why and how we might want to use this. So the first scenario we have in mind is close to what I really did in the introductory example. That's you have a voting rule that's fixed by some law or by some agreement. That's going to be the one that will be used to compute the election outcome. But maybe not everybody who voted or who looks onto this process completely understands the rule. Maybe not everybody completely agrees with the rule. Maybe not everybody was asked for the opinion when people agreed on using this rule. So people are kind of a little bit suspicious about this. And many of you will have experienced that yourself. If you know, sometimes people ask you, okay, so tomorrow we have this committee decision. You know about voting, so what rule should I use? And then you come up with something. And if it sounds a little bit too sophisticated, then the follow-up question is immediately, okay, so but won't that the other people then be able to exploit that and so on? So people don't completely trust these kind of things. Having these kind of justifications might allow us to independently of the voting rule give good arguments to people why this is a good outcome. Edith, your question is long, so I will answer it later. The next idea we have in mind is deliberation. Did the slide come? the slide move? No. Bad. Sorry, I'll try again. Now it did move, yeah. All right. So the next idea is deliberation support. So there are people who just together want to come up with a good decision. They have their initial preferences. And they would ask these justification mechanism to say, okay, given what we currently all say, what would be a good outcome and why? And then they would be able to look at that data, at these suggested justifications, maybe different justifications for different outcomes, and they would be able to compare those, each possible outcome that can be justified somehow together with the axioms and the quality of the explanation that justifies it. And it would maybe help them to come up with a good decision. And the next one is that we can use justifications themselves maybe also for voting. So the idea is the following, that we have a big set of axioms, maybe way too many, that together would be highly impossible to find a voting rule that satisfies all of them. But we put them into little sets of axioms and say, well, if I can justify something with these axioms, I really like it. Try that first. If that's not possible, take this little set of axioms, try to justify something with that one. Then you have a kind of sequence of these sets, and you try to find a justification for an outcome with the set of axioms that you like the most. So with this explanation, is anybody able to solve this exercise over here? To kind of guess what the notation means. So it seems to be a voting rule that is somehow generated by two sets of axioms, and there's a correct solution indeed from Marcus, very good. So what this one says is, if you're able to justify an outcome using the Condorcet principle, go for that. If you're unable to find any justification with the Condorcet principle, try this other set of axioms: neutrality, reinforcement, faithfulness, and cancellation, which happens to characterize the border rule. So that means in that case, try the border winner. And this is something that some 70 years ago, Duncan Black actually suggested as a voting rule. Okay, so these are the scenarios. Then I want to very briefly talk about algorithms. How can you actually compute these justifications for any given set of axioms and input profile and set of winners that you are considering. So the first idea, and I'm going to do this on one slide, so I will be a little bit abstract and high level about this. The first thing is that, like in some other work that some of you may be aware of, it can be sometimes possible and interesting to try to encode some of these aspects of axioms, in particular some instance of axioms, in propositional logic or some similar finite language. And that's possible if I don't want to talk about the axiom in general for every possible electrode, but I just want to talk about what does this axiom say for one particular profile and one particular set of alternatives and things like this. I can write that down as a possibly very long formula made up of little atomic propositions like this. So these are little variables that are true if X is a winner in this profile and it's false if it's not. So in principle, you can write anything you want about voting rules in that language. Might just be very long and cumbersome to do that. So the basic idea is that we write down from our big corpus of axioms every instance in this kind of encoding, plus one more formula that says this set X star that I'm interested in is not the winner. And then if that gives me a contradiction, then it must be the winner. That's the basic idea. So if all of these instances together with that still is something that's satisfiable, then I have failed. I have not found a justification, because it's possible to satisfy all of these axioms without X winning. But if it's not satisfiable, then I might be able to find a justification as follows. I will then look for a maximal unsatisfiable subset of this set of formulas that I've generated. And I'm going to call most of it, everything except for this goal constraint, my explanation. And so that means then the goal constraint and this explanation together just about gives me a contradiction. So just about says that they just about say that X star really must actually win the election. And then finally, I still have to check that I'm not fallen in the trap and done something trivial. I have to check that the formulas corresponding to the full axioms that I have used in my explanation should still be satisfiable. There should still exist some voting rule that would satisfy all of these axioms. So you can imagine that's super complicated and complex in every sense of the word. So that's potentially bad. We have been able to make it work for small examples so far. And the reason why we have been able to make it work at all is that we, the really hard work is done like here, for example, you're checking satisfiability, you're computing a maximal unsatisfiable subset. These are standard problems in constraint programming, the SAT solving community, where people have been working on for a few decades on coming up with really, really good algorithms. So we don't have to solve all of these problems ourselves if we are able to map our problem into this. I'm close to finishing. So there's a chance that this might work. One more slide before the last one. I want to say a few things about possible directions for future work that I think are interesting and that we have not at all been able to look into ourselves so far. And I think that's something that maybe also other people want to get involved in. So we've only done this for simple single winner voting rules, irresolute single winner voting rules. The same question in principle you can ask for pretty much any social choice framework. So certainly for multi-winner voting, also for matching, for judgment aggregation, maybe for fair division, it would make sense. I don't know all the details whether they're going to work out so nicely, but there's a good chance. I think it's interesting. It's definitely interesting, number two, to work more on algorithms. So we have used SAT and constraint solving. SAT has worked a little bit better in practice. Constraint solving, we have some soft spot for it on the theoretical side. I think it offers some nice potential advantages that we have not been able to fully exploit so far. There might be completely other ideas for doing this kind of stuff. So the algorithmic side of it, I think there's still wide open and lots of things to do. The cognitive angle. So we have a pretty technical social choice theoretic definition of justification, but you could ask, okay, which of these ones will people actually like? Which ones will they find convincing? There's a whole psychological aspect to this. And a broader research agenda, a little bit outlined with this in this old paper with Olivier Caillou a few years ago, is that it would be interesting to use computer support, like in this example, to help people to think actively about voting rules. What's a good voting rule? Why is it a good voting rule? Should we use a different one? Jumping between examples, explaining stuff and so on. And this is just one aspect of that. Okay, last slide to conclude. So I've given you a little bit of an insight into this idea about axiomatic justifications we've been working on. The slogan is justification is normative basis plus explanation. So normative basis, set of axioms that you like, explanation, kind of proof that shows that the axioms do the job. We've talked a bit about algorithms. I've talked a bit about the different kind of scenarios that you could use, and talked a bit about potential for future work. The paper, Vince already put it in the chat. It's on the website. It's on our websites as well. It's easy to find. And actually this morning, a nice person at our institute published a little video about this paper. So then if you want to see the same thing again with cartoon figures like this, you have the chance to watch the video. Thank you very much for your attention.
Okay, thanks, Ulle. Let's unmute ourselves for a round of applause. There's been lively conversation in the chat. I was the first to ask the question, and I suppose I still want to have it answered, but I'll deprioritize myself. The next person to ask a question, I think, was Umberto. Umberto, do you still want to ask this question, or do you feel it's been answered?
So I just want to very quickly say that I think the last slide again you didn't see, so I'll show it to you for 5 seconds, and while Edith is finding a
right, and in particular, I think it conveniently addresses Umberto's question. Okay, so let's.
Is there a movie? Was the question?
Right. Okay, so that was Umberto. Okay, so there was.
Do you have a recommendation which one I should go for?
So there was a
I'll just pick a random one and read it.
Which I can read out. Bill asks, I might find some particular instances of an axiom more compelling than others. This suggests that your framework might serve as a basis of deliberative process. in which we observe a profile and debate compelling instances. Have you considered this?
Yes, so very, very good point, yes. So indeed, you might find, for example, you might find the Condorcet principle generally very appealing, but in a few special cases, a little bit weird what it does. So here you might disagree with some explanation that uses certain instances of Condorcet, and you might agree with other ones. And this framework gives you the freedom to have that conversation.
Now there's a question from Nisarg, which I think is somewhat technical, so should be easy to answer. Ulle, can you find it? Do you want me to
yes, so I think it's this one. Since some of the axioms, such as reinforcement, apply to profiles with different sizes, checking whether a set of axioms is satisfiable could require considering instances of all possible sizes. Is that something that can be done with such styles? Yes, very good question. So indeed, the reinforcement axiom in the full classical sense, I will tell you about another sense in a moment, would cause problems, because this one, I mean, the intuitive use of reinforcement is that you have a big profile, you're looking at the sub-profiles to learn something about your current profile, but the axiom also speaks actually about the profiles above you. And in some special cases, you might really need to look at that. So the SAT approach will indeed only work if you up to a certain limit. So you may say, I want to look up to profiles of whatever size, and you could always be missing something. Now, we are not considering this a major problem, that it's a little bit technically difficult to do that. The major problem we think is at the cognitive side. People will just not find an explanation very appealing that says, in this little profile, A should win, because in this other profile with 100 people, B was winning. So people will not really be interested in those kind of answers. So that's the technical difficulty that we do have. Is really just a reflection of the actual difficulty. So we have in the paper, we have a reinforcement star axiom, which only looks down and which is weaker and which doesn't do everything that reinforcement does.
Okay, then there's a question from Marcus. Would it also make sense to allow incompatible sets of axioms for explanations?
Yes, would it also make sense to allow incompatible sets of axioms? Absolutely, and I think this is one of the interesting things. So if you only put in the axioms that are mutually consistent and, for example, correspond to a specific voting rule, maybe border, then all you're ever going to do is justify border winners. I think what's more interesting is that you have a larger set of axioms, so all the border axioms and Condorcet and something else, and you can choose in this particular situation, maybe Condorcet and reinforcement don't actually contradict each other. So you might get a very convincing explanation for this particular situation. Well, okay, so you have to be careful. So you have to be careful that you're not in an actual normative basis put axioms that then really contradict each other, but you could have in your corpus, you could have axioms that contradict each other, and for different situations, you use different ones. So today I'm going to use Condorcet because I find it easy to give an explanation. Tomorrow I use reinforcement because I find it easy to give another explanation.
Okay, so I'm going out of order now, but yeah, so perhaps the last question by Martin Bullinger.
Yes, okay. In a specific voting rule in the knowledge base, if a specific voting rule in the knowledge base has a certain outcome, does there always exist a justification for this outcome? Yes, okay, so yes, so if I have a particular voting rule and it would produce winner A, if I know an axiomatic characterization of this voting rule, and if I'm able to encode those axioms, if I, for example, don't have this technical difficulty with reinforcement where there could be a problem, then yes, I would exactly reproduce the voting rule, what the voting rule does.
At the end of the time slot, so Ulle, would you like to, so there's a couple more questions. So
I'll pick a couple of quick and easy ones. So Gabriel, can you handle axioms that compare the outcomes of two different profiles? Like a monotonicity axiom, yes. So we have, for example, we have implemented neutrality and anonymity, which are of this kind. We have not implemented, I think, when I say we, I mean Arthur has not implemented monotonicity, but this is possible in principle, yes. There are no, reinforcement even refers to three profiles, and this is also possible in principle. Vince, if we like some axioms better than others, should I do this one or not? I'll do it quickly. If we like some axioms better than others, can we turn it into a constraint optimization problem where every axiom you use comes at some cost? Yes, I think this would be an interesting variation of the third scenario that I've talked about, that you say, yeah, using this axiom has a cost, and you try to minimize, you try to find a justification for a outcome that is as cheap as possible in terms of, you know, the bad axioms that you have to use. And you might want to factor in other things as well, like maybe the length of the explanation. Maybe you don't like long explanations. Maybe you favor short ones. So how I explained it was just one very simple version of this general idea. Thank you.
Okay, I suggest that we stop here and thank Ulle once again. I don't know if everyone agrees. I feel there was some sort of synergy between the two talks that we had today, which I can't quite formalize, but I think they came together really nicely. Okay, yeah, so thanks everyone for coming today. So now Dominic will say a few words about the next week's seminar that he will be chairing.
All right, thanks, Edith. Next week we have talks by Bettina Klaus and by Omar Lev. That should be fun as well. We are slowly starting the summer season, which means we will have seminars less often over July and August, and we'll then restart again properly in September. We will then also switch to Thursdays, very likely as our standard day. Right, but for now, I'll see you again next Friday, bright and early, or in the afternoon, depending on where you are. All right, thanks.
Bye-bye.
Bye.
Bye.
Okay, bye.